Here we go. Let's start today. All right. Glaciers, because everybody in Southeast Missouri knows everything about glaciers there already is. Um, very, very new. Scale is something we'd have no context of. We think of ice. We think of thin ice. Glaciers are massive. Ice sheets are massive, even more so. Glaciers are not thin little things. This is the end of a glacier coming down through there, and you can see the people in the foreground. All right. Pretty pictures. Pretty pictures. Huge, huge glacier cutting across here. Very thick. You could probably see this little ship in there. Mountains. Whole thing. Glaciers are big. This is another valley glacier. It's coming down the valley, cutting that used to be a stream, and now there's, So here we go. The glacier is just a thick ice mass that forms over hundreds of thousands of years. It doesn't happen. It lasts. I guess it forms over 100,000 years is maybe a little misleading. It persists because the glacier is constantly moving. Ice moves. It's weird. And it's changing and it's growing or shrinking, or maybe it's staying the same, but it's dynamic. Okay? So we're going to leave that valley glacier up. There's another valley glacier coming down the mountain. That's a nice Wikipedia page there. All right. Here, National Park Service says, look, there's a pretty glacier coming down. Very cool stuff. All right. In fact, you've got several of them meeting here, and you got this ridge along here. That's a thing we're going to talk about later. Okay. 15,000 years ago? 1,000. Not that long geologically. When we did geologic history, geologic timeline, 15,000 was nothing. That was about the end of the last ice age. Round numbers. Before that, going back to the Pliocene, with the woolly mammoths and saber-toothed tigers, yeah, those glaciers actually started like 2 million years ago, and they lasted, and then about 15,000 years ago, they retreated to more of what we would consider a normal or current state. 30% of the world at that time was covered in glaciers. Now it's about 10%. When we say of the world, glaciers don't float out in the ocean. Those are icebergs. Those are different. Glaciers form over land. So 30% of the land was covered. Now it's about 10%. Okay. Here. At the end of that 15,000 year, this is what we're talking about. That is all of this. This is the North Pole's dead in the middle. All right. So you've got Europe, Russia, wrap around, Alaska, Canada, New England, Greenland, right? Greenland. Now, you could see what's going on from the North Pole and the distortion of the lower half of the map. Odd to see it like this. Then, now. And some of this sea ice melts seasonally. All right. One more reference, quick thing. How thick were these ice sheets? That's the one thing we think of, just, 20 foot thick across that whole. No. Ice sheets across those continents. This is 21,000 years ago. That's 2,000 meters. And there's Toronto's modern skyline, Chicago, Boston, Montreal. All right, and then we do this. It highlights. It gives you the citation and the little joke about the citation, if you know Randall Munroe at all. Anyway, the ice sheets were huge. In fact, we're going to talk about the one across Antarctica is huge. Thick. There is no rock and dirt under there. This is not a mountain with a layer of snow. That's the misconception a lot of us have. Oh, it's a mountain. It snowed on top of the mountain, and so the top looks white. That's snow. This is an entirely different thing. And that's what we've got to build to. All right. Snow line. So what's the snow line? All right. Well, you may have heard of a tree line before, but the snow line is this. Maybe it's right here on this mountain. Okay. It says, look, it snows and all of this is covered in winter. And then in spring, this bottom melts, but the top is still high enough that it's cold. It stays frozen. Melts, frozen. And that line right there that says this will always stay frozen above here and below here will melt seasonally, that's the snow line. It's different for every mountain. It's different for every location. It's different across, but it's a regional thing. So that's the snow line. So it's the lowest elevation in an area that remains frozen. Okay. At the poles, North Pole, South Pole, the snow line is sea level, meaning that if it ever snows, it's going to stay cold. Summer, winter, spring, fall, it doesn't matter. It's not melting. Near the equator, you've got to go way up on top of a mountain to have any type of permanent year-round snow cover. Okay, that's just snow. Remember, that's just snow. But it snows once and doesn't melt above the snow line. The next year it snows and doesn't melt above the snow line. The next year it snows and doesn't melt. As you accumulate this snow, it packs down and compresses. And that compression forms a type of ice. Okay? So, the compressed snow recrystallizes. That's the word I was looking for. Into rough, coarse grains of ice. If you keep piling more on, all right, more pressure changes the coarse grains into interlocking crystals. And those are glacial ice, right? This is not snow. That's snow. This is a chunk of ice put together by years and years and years of pressure crushing all of this together, and it's cold and it's going to melt. It's recrystallize. It's going to change into form and make a glacier. That's what a glacier is. It's the buildup of all of that. Cool. Two main types of glaciers. Valley glaciers that you see on the screen and ice sheets. Antarctica, Greenland. We saw a couple pictures of. Do not have a caption for this. National Park Service. This is in Alaska. Okay. So, ice sheets again. All right. Focus. Here we go. What you have is you have snow. Glaciers move down the mountain in two ways. There's plastic movement and there is slip. Let me get my word here. There's it's not basaltic slip. It's basal slip. It's basal slip. Okay. So plastic deformation has nothing to do with plastic, the material. Okay, I want you to think for a second. Think of a paper clip. If you grab one end, I don't have to think. Look, it's a paper clip. All right, so if I grab this end and I bend it out a little bit and I let go, it springs back. If I let go, it springs back. If I let go, it springs back. That is elastic deformation. If you have a slinky, or a spring, you can bounce it around and it springs back to its original shape. If I bend this out a little bit, that is plastic deformation. It's not elastic. So that's the way the material reacts. I didn't break the metal. I didn't change it its elements composition. I didn't heat it. I didn't do anything to it. But it bent differently because now it doesn't spring back. That's what plastic deformation is. And I can't get it back exactly the way it was. So plastic deformation happens in the middle of a glacier. You have to be at least 50 meters down so that the pressure on top of the ice is great enough that it squishes and slides, and there's enough pressure to deform it, and it will slide down the mountain. Up at the top, you get an accumulation zone. You add snow, you add snow, you add snow, you add snow year after year after year after year. You're building, and it's going to slide down the mountain. And when it gets to the bottom, it's going to melt because it's below the snow line, or it's going to calve off and make an iceberg. So you're adding, you're losing, you're adding, you're losing. And the only way you can keep this getting down here, the whole thing is sliding down the mountain. That is basal slip, where the top layer, the top 50 meters, is under much lower pressure. It rides on the middle and the lower half of this, even piggybacking on this. All right, plastic pressure, minimum 50 meters. The whole mass slides down the hill. That's the basal slip. I already said that. Upper zone. The top zone, the top layer of this stuff is more brittle because there's not as much pressure on it. It's just ice, right? Ice cracks. We drop an ice cube, it cracks. No big deal. But as you're going over uneven terrain, you can get crevasses because the top layers aren't hooked together that well. And so as the bottom slides over something uneven, the top layers split open. So that could fall almost 50 meters down. Very dangerous situation if you're out on a glacial field or on a glacier somewhere, because you put a little snow on top of this, cover it up. It would be easy to just walk across the snow and whoop, they are dangerous. All right, that's for in a minute. That we're kind of look at. We're going to leave that one up. We don't need the rest of that one. And that was just a pretty picture again. All right. Glacial budget. I don't know how to say this. So, how much snow did you get in a year? How much did you add to the top end? How much melting did you have that year? How much did you take away from the bottom end? That overall determines the size of a glacier. You've got to wait years and years and years for this to add up. Because if you get 1.5 inches of snow and you melt the bottom, lots and lots of snow in these regions, and it's over years and years and years averages. Those are a lot of the end pieces. I'm missing some of this. All right. So snow, granular ice, and then it's talking about the compressed ice and different things. How you slowly compress the snow year after year after year. All right. How these things move down the mountain. The speed varies a lot. Okay. Depends on how much snow, how long, how steep, how wide. All sorts of things depend on this. Okay. This at the bottom is the zone of wastage, where it either melts off or breaks, where you have more spring melting than you have ice pushing into an area. And now this line can stay stationary year after year after year after year, as long as you're adding as much up here in the mountains as you're taking away down in the valleys. All right. Glaciers erode lots of stuff. Glaciers move. If you ever look at a glacier, they aren't like fresh fallen white snow. They have junk in them. They are full of rock and debris because they work just like a stream. They carry everything downhill. They erode and carry everything downhill with them. Couple differences between a glacier and a stream. One's frozen. Yes. No. In a stream, as the stream slows down and speeds up and slows down and speeds up, the size of rock it has changes, right? As it starts to slow down, the big rocks fall out, and then it slows down a little more, and then the medium rocks, and then it slows down, and finally, then the small sand settles out. Glaciers don't have that. The sand, the medium rocks, and the big rocks are all moving in this frozen mass, and they all get to the bottom, and then it melts, and they just all drop together. There's no sorting of the till in a glacier. Okay? So there's two ways to erode this stuff. As this ice is moving down here, you can pluck or you can abrate. So plucking is, the water melts little by little. It gets into the crack in the rock over here, and then it's going to break a chunk, refreezes. It breaks a chunk of the rock off, and it plucks that rock, and that rock comes with it. Whether it's on the side or on the bottom, doesn't matter. Abrasion is grinding, because this isn't water. Frozen water is hard, but it's also got rock and other things in it. And as it goes down, you can see rock in glacial zones that have huge scrapes across them, because there are tons and tons of frozen water here grading across everything underneath it. And it's going to take what used to be a V-shaped valley and make it a big fat wide U coming down there as a glacial valley. That should be that one, that you get this big wide U-shaped valley. Couple other things you can get. You can get hanging valleys. You can get cirques and arites and peaks and or horns. Okay, when this is full, if this is full, this huge valley right here is a full glacier all the way up to here. And that's a glacier, that's frozen, that's frozen. Now, if it melts, this doesn't dig any deeper when it's all frozen, because the glacier hits this glacier and then all the snow goes and ice goes together. Same here and same here. Then this melts. If it all melts because of something, then you have this huge stop. This is a hanging valley, because this smooth valley that used to run into something now runs into nothing, and you've got this waterfall. There's waterfalls in Yosemite that are based on this, okay? Some waterfalls are based on glacier melting. What used to be part of North America covered in a glacier melts, and now you've got this mountain coming down and then this huge waterfall into a big trough. All right. Let's see some of the other things. The cirque. The cirque is the head. It's where it starts. So you've got this big bowl. You've got three sides shaped by rock. It's the head of the valley. All right. It's the arite is the snaking sharp edge right here. It's the edge of the valley. The cirque, the arite. These are prominent in the northern Rockies, the Alps. So is the horn, is the almost a pyramid shaped peak up here. Let's see. What else? Okay. Now, that's at the top. What about down at the bottom? The till, the drift, all the stuff that moves downhill. The till is the stuff deposited by glaciers. You can have where am I? All right, moraines. There are lateral moraines. Okay, these are on the edge of the main. This is all in the deposit area. We're all downhill. Deposit features. All right. These moraines run along the outer edge. The medial moraines run in the middle. All right. The end moraines actually go sideways across here, because it's going to pile up. All the stuff's going to pile up here, and then the glacier's going to retreat, and it's going to form a new pile, and it's going to retreat and form a new pile, and on and on and on and on and on. So as it brings stuff down the mountain, all that stuff it brings down builds up in a pile. If the glacier is slowly retreating, as it melts more than it brings down, then you're going to get it back piles backing up. If it's advancing down the mountain, if it's snowing more than it's melting, it's going to keep pushing all of this stuff down here. All right. So the terminal moraine is the outermost. These are recession lines. All right. You've got outflow plains. Let's go over here. Outwash plains. The outwash plain is the stream, because the stream of meltwater doesn't go very fast, and you're already down the mountain, so it's kind of flat, so it's real slow. It can't move a lot of stuff. It can't move big rocks. So it's slower. It meanders a little more. Things to think of like at the bottom of a river, not coming out of the valley fast and moving quickly. What's over here? All right. Some of the other things you can get. Um, all of this. So as the glacier retreats, you can get all sorts of mini lakes. Outwash Plain is out here. Uh, these kettles are mini lakes. All right. Yep. There's just a depression. It's a small lake in the Outwash Plain. This esker right here. While this glacier was here, if there was water melting under it, that water moving underneath, making a tunnel, coming out and forming a little stream, that's an esker. Well, I'm going to take that back. Yeah. The esker is not the water. The esker is the sand and gravel left behind or on the edge of that stream. Because as this glacier melts, you're going to have less and less and less water. And you're just going to have like this little ridge of sand and gravel left that had been carried by this melting water from underneath. And it's just going to be this little bitty ridge of sand and gravel. So it's not the water, it's the leftovers. All right. These drumlins are hills that are in a field, but they're all kind of oriented the direction this is moving backwards and leaving. All right. Some of these lakes, the Great Salt Lake used to be Lake Bonneville. It was full. As the glacier retreated, and now what's left, it's evaporated, and shrank, and now you've got the Great Salt Lake. There's a lot with glaciers, and they're very unfamiliar with us. They're very, very, very tall, and that's the first thing. It is not a mountain of rock with snow on top. It is ice from bottom to top, and absolutely could be the same height. The glacier over Greenland is on average 1,500 meters. Now, the glacier over Greenland is the ice sheet, right? It's not a valley glacier, it's an ice sheet. 1,500 meters is just short of a mile. So instead of a rock mountain at Denver, the average height of ice across Greenland is 1 mile high, just about. All right, it's good to learn about glaciers. There may be a simulation coming up with this. Have a good day.